Testing. Okay, good morning, student. Welcome to join our class again. This is lecture 8 for our module Theory of Structure 2. Well, first of all, maybe we can wait for a few minutes. I believe that some student may join us later. And during this time, we can have a short revisions about what we have right now. This is our Moodle page. For your information, I uploaded our assignment 1 solution on Moodle. If you want to know how I solved the 3 problems, you may have a look in the solution. There are also some explanation in the document, help you to understand the solutions. And I think last week we start to discuss structural dynamics, which is another area for this module. If you still remember, in this module we have totally 3 big chapters. The first one is Sylvus method. We have already completed the discussion of Sylvus method. You may call this matrix method because Sylvus method relies on many matrices. And then we start structural dynamics. You can see the dynamic is quantum mathematics. It's involved the solving the differential equations, involve you to understand how to interpret the result, displacement, etc. We will learn more in the future. In topic 4, we discuss some formulations. It's good to understand all the questions in topic 4 because later on in topic 5, topic 6, topic 7, sometimes I just directly recall the formula. I mean the equation of motion from topic 4. And then last time we complete topic 5, free vibrations. Free vibrations mean there's no any applied loadings, no loadings. And then last time we start to talk about forced vibrations, structures with loadings. Today we will complete our journey to complete all the things within topic 6. We still have I think 1/2, did not finish last time. And then hopefully we can also enter a new topic, topic 7, about numerical methods, which can help you to handle a more general situations. Okay, this is where we are at this stage. Another issue is that we has already conduct all our SAP 2000 workshops. The last workshop has been completed yesterday. I will upload our SAP 2000 assignment very soon on Moodle. So yeah, just for your informations. Before starting our class, is there anything you want to ask me? If no questions, then I will start topic 6 again. No questions, then it doesn't matter. We can continue our discussions. This is topic 6, forced vibrations. Let us have a short revisions. Forced vibrations mean structures, a single degree of freedom. At this stage, we're still talking about single degree of freedom structures. For all single degree of freedom structures, you can finally put down the equation of motion in this manner, no matter how it looks like. It may look like a frame, it may look like a beam, it doesn't matter. You can always convert them back to this ball and stick model. You just find out the equivalent mass, equivalent stiffness, equivalent damping coefficients. Then mathematically, for this ball and stick model, the corresponding equation will be looked in this manner. mu double dot plus cu dot plus ku equal to force. Force can be any kind of force. Dynamic force for sure. For static force, there is no need to use dynamics concept. Last time we paid great attention on these particular situations, harmonic excitations. Harmonic mean, in theory, harmonic means sine or cosine in theory. But normally we use sine function as an example to discuss the structural response. If you like, you may also solve it using cosine force, but sine is more common in our discussions. And then last time we discussed how to solve the problem, how to solve the equations. If you forgot, you may go back to the videos on Moodle. I cannot complete all the review all the things. I just show you the solutions. If you had attended the math module, then you should notice that this form is called non-homogeneous differential equation. Non-homogeneous means the right-hand side is not equal to 0. Then the solution should be composed of two parts, homogeneous part and particular part. This is the math understanding. But in terms of physics, I think it's always good to understand physically the meaning of each part of the solutions. Physically, it means it has transient response and steady state response physically. Transient response means it's a that short period of time. Transient means temporary. It's appeared only at the beginning. Whereas steady state means it will appear forever, always there. Why transient response will disappear later? Because mathematically, you can see this exponential function. This exponential function, we call it decay function, which will make this part disappear when t is large. So we call it transient. Steady state response, there is no exponential function, so they will be here forever. I think it's good to understand physically the meaning of homogeneous part and particular part. If we want to answer the questions in this section under harmonic force, normally we use the steady state response because steady state is our interest. They will be here forever for structures under a sinusoidal force. There are many equations for structural dynamics. Free vibrations, you have a set of equations, right, in topic 5. In topic 6, under harmonic loadings, you have this kind of equations. As I mentioned before, you can use the equation directly without proving it. You can use this kind of equation directly. You don't need to prove it, but use it properly. Choose the correct situations. This situation, steady state response, is under sinusoidal force, harmonic loading. Okay, don't use the wrong version. Last time you have another equation, right? For under free vibrations, you have an equation something like a cosine plus b sine, and then exponential function, something like that. This one is for free vibrations. Okay, for structures under sinusoidal force, the equation at steady state look in this manner: UST times RD times psi something. Use it properly. RD is called dynamic magnification factor, and then phi is the phase angle. They are calculated using two numbers: beta and damping ratio. Beta is called frequency ratio. Beta is called frequency ratio. The exciting frequency of the loading versus the natural frequency of the system. Natural frequency, you can calculate natural frequency yourself based on stiffness, based on mass. You can calculate stiffness. You can calculate natural frequency yourself if you know mass, if you know stiffness. So you can calculate this RD directly if you know these two numbers. RD we call it magnification factor because from the equation it seems that it's just like a factor multiplying with our static values. Our static value is equal to the force amplitude over stiffness. RD tends to amplifying the response or decreasing the response based on the exact number. If the number is greater than 1, that means it is amplification factor. If the number of RD less than 1, that means it's something like a reduction factor. We also have some discussion about the meaning of RD and phi last time. You may have a look of these few pages. I'm not going to repeat. This graph is useful. We call that frequency response plot. This graph helps you to understand how RD change with frequency ratio. This graph helps you to understand how it's changed. At the beginning, the value of RD is 1 when frequency ratio is 0. And then you can see that RD start to increase as frequency ratio increase up to maximum number at approximately equal to beta equal to 1. We call that resonance response when beta equal to 1. Approximately equal to 1, not exactly. And then when you go further, then the values of RD start to decrease and then reach approximately equal to 0. At beta become a large number. This graph is important to show you how it changes with different frequency. And you have to also pay great attention on this graph for situations under high damping. Under high damping means damping ratio exceeds 0.7. You can see that from the graph, we can see that there is no peak value. There is no peak value, even though at resonant frequency, you cannot see the peak for a system with large damping ratios. And then we complete this part. We last time we talked about a few applications. We discussed the first two. We discussed how to generate the harmonic loading using vibration generator. And then we discussed a little bit how to measure damping ratio using harmonic vibration response. This one, vibration generator, just for information, how to generate a sinusoidal force. You can use a machine like this, attached by two masks. When these two masks rotate, it will generate a sinusoidal component. You may put it on a structures, on a force slab, on a beam, on something to generate a sinusoidal force. Last time we mentioned there are two methods to measure damping ratios based on harmonic response. The first one is resonant amplification method. The other one is half power bandwidth method. They also help you to find out damping ratio. Depends on what information you have, right? These are what we are last time. And today we start from our third applications. Today we start from here, our third applications. After knowing the harmonic vibration response, there are several applications. One is using measured damping ratios. And look here. Here we can use the concept of harmonic vibrations to develop some machine, some device, help us to measure acceleration or measure displacement. If you develop a device to measure acceleration, we call it accelerometer. Accelerometer, acceleros is something like acceleration. Meter is something used to measure the values. Accelerometer means a device used to measure acceleration. For earthquake, we normally represent earthquake using ground acceleration, right? We mentioned in topic 4, ground movement. How to measure ground accelerations? Well, you can use accelerometer, put it on a table, put it on the ground, put it on some stations. Then when earthquake attack that region, then these accelerometers will give you some value, some reading, something like this. If you know the acceleration history, then you can use it to do some prediction. You can record the data for future applications, etc. Quite useful. Similarly, displacement meters mean a device used to measure displacement. Then how we can apply our concept? I mean, using the harmonic vibration concept to set up this kind of meters. We will discuss in this section, section 3. There are two devices right here, accelerometer, displacement meter. In this module, we basically focus on the first one. You know, in the quiz examination, in the examination, sometimes I may give you some essay type question, not necessary to be all calculation for exam. For exam, I can ask you some essay type questions. I may ask you, hey, what is the mechanism of accelerometer? Then maybe this part may help you to answer that kind of essay type question, if any. We normally focus on accelerometer in this module, not displacement meter. That's why I turned the displacement meter in gray color. But the principles are quite similar. The principles are quite similar. How to use it? And you can see from this picture, a simple mechanism of accelerometer, just like a spring mass system. A mass, a car, attached by springs and damper. So for this kind of system, we call it spring mass system. You can model it using equation of motion, immutable dot plus zero dot plus ku. Actually, it's something related to our discussion in the previous sections. Assume that an accelerometer is just like a spring mass system. You can imagine that this is the machine. There is a pointer here, a pointer attached to a scale on the top. When this mass display horizontally due to earthquake or due to the other ground motion, When this mass displays horizontally, the pointer will shift back and forth above the equilibrium positions. The pointer will show you the corresponding values. So it seems that a accelerometer can be represented using something like a spring mass system, which can move horizontally. For spring mass system, the equation of motion always in this way: mu double dot plus cu dot plus ku equal to minus mu double dot g. I hope you still remember this equation. This is the equation of motion for structures under ground accelerations. If you forget, you may go back to topic 4. Topic 4. The last sections, we discussed how to formulate equation of motion under ground accelerations. I think last time we used a picture like this: a structures with no force but underground accelerations. Something like this. And then we mentioned that for structures underground acceleration, the force part, the force becomes minus mu double dot g. G is the ground acceleration history here. U double dot g is the ground acceleration history. Let's have a look. Well, in reality, the ground acceleration history is arbitrary. So there's no, it's not sine, it's not cosine. In reality, the ground acceleration is arbitrary function. It's not sine or cosine functions. But let's consider a more simple scenario. Suppose the ground acceleration is a very simple function like a sine, a sinusoidal functions, sine omega bar t, and then the ground acceleration amplitude is u double dot g 0. Okay, we make things simple. Assume that the ground acceleration is a line function, a sine functions. For a structures under a sine functions, a sine loading, it becomes a sine force. If the loading is a sine function, this equation is equivalent to what we learned in the previous sections, structures under harmonic loading, right? If it is a sine force, then we know the steady state response for these structures. The steady state response is equal to what? UST times RD times an oscillating function. For a sinusoidal force, the steady state response always look in this way. You just need to use this equation, find out what is UST, find out what is RD, find out the sine function, something like that. I directly copy the steady state solution from the previous part. Minus mu double dot g0 over k times RD times this sine function. Okay. And what is UST? UST is equal to the force amplitude. Maybe I put one more step here. Minus mu double dot g0 sine omega bar t. You can see that the coefficient before the sine function is minus mu double dot g0. So this becomes something like our force amplitude. You may group this into one term called P0. UST, by definition, UST is equal to P over K. That's why you can see that UST is equal to minus mu double dot g0 over K times RD. RD, we have one equation before. RD depends on two parameters, depends on beta, depends on damping ratio. RD, these two. We have one big equation with square root something, sine equation. And then I rearrange the equation a little bit. Say, for example, I group those coefficients m, k into one terms, also RD. And then I move the ground acceleration outside this bracket, and then sine function. This is the displacement of this spring mass system. What is the meaning of displacement? Oh, I erased the picture. As I mentioned before, this spring mass system has a pointer. When this mass displays horizontally, the horizontal displacement is denoted by u. This u is showing the scale of the earthquake. When the mass moves left, then you will see the pointer move left and give you some reading. The reading show you the value of the ground acceleration, something like that. But for sure, you have to do some calibration. You have to set this scale properly to see what is the corresponding unit for this scale. You have to do some calibrations. But the mechanism is like this. The movement of this mass can show you the value of the ground acceleration, something you want to measure. Okay, so we call it accelerometer. The thing is not that simple because we still have something to evaluate. Say, for example, you have to find out what is mass, what is k. Otherwise, you cannot correlate the displacement and accelerations. M is the mass of this machine. K is the stiffness of the spring of this machine. This machine, accelerometer, is set up by you. You are the developer. So you are the manufacturer. So you can measure the mass, you can measure the stiffness yourself because you can set the mass and K yourself. Right? You can use a proper spring, you can use a proper mass to make this accelerometer. So MK, they are two well-divided numbers. They are not unknown. They are not unknown. You can find out the values. You can set the value yourself. So MK is not unknown. You can find out at the beginning. So it seems that RD is something that you want to evaluate. If you know RD, then you can find out the relationship between displacement and acceleration. Acceleration is something that you want to measure. Displacement is something that you can see. So the correlation factor is this gray color. RD, MK you can calculate and you can evaluate, but what about RD? RD means dynamic amplification factor. I put one picture on the top right-hand corner, show you the values of RD. I just copy from the previous sections. You can see that RD, in theory, RD is not a constant. RD value change with different frequency ratio beta. So it seems that this equation for displacement, the relationship between displacement and acceleration seems to us that it's not a fixed number because for different RD, you may have different proportional constant. But we have one very interesting observations. When you consider a very extreme scenario, how extreme? Assume that you consider a large damping system. Damping ratio is large. Say, for example, 0.7. Again, this is a machine that's set up by you, so you can tune the damping ratio yourself. Now I consider a system with large damping, 0.7. RD is RD, not R. RD is approximately equal to 1. When you talk about low frequency range, frequency ratio less than 0.5. Take a look on the graph on the top right-hand corner. Consider the green curve. Small damping, small frequency ratio, which means here, this region. You can see that in this region, the values of RD is approximately equal to 1 within this low frequency range, 0.5. So we have this conclusion, RD approximately equal to 1. And therefore, according to this displacement function equation, it seems to us that the movement of our mass, the movement of our accelerometer is somehow linear proportional to the ground acceleration, linear proportional to something that we want to measure. This one you can tune this device yourself so that the displacement can reflect the ground acceleration. Okay, this is the mechanism behind accelerometer. You need to tune the parameter so that the displacement can use to reflect the ground acceleration of an earthquake. Okay, actually, I just want to mention that this machine is not applicable for all frequency range. What I want to show you here is that, it seems that this machine only works for some certain assumptions. The assumption is that the frequency is not that high. The frequency is not that high within this region. Just let you know that normally you have some device to measure different quantity, acceleration, velocity, displacement, but normally they have some applicable range. Within the range, they're accurate. Within the range, the value is accurate, can represent the ground acceleration, etc. But outside the range, the value is not that appropriate. So when you use the device, you have to read the instruction carefully to see the applicable range. Okay, this is something that I want to mention. This slide gives you some reference about what we just go through. And we consider one device as a accelerometer with natural frequency equal to 50 Hz, damping ratio 0.7, large damping. This is some data of our accelerometer. The natural frequency is 50 Hz. And then on the right-hand side, I show you the corresponding result. We want to use this device to measure ground acceleration with different frequency. The first picture, picture 1, show you a ground acceleration with frequency 40 Hz. The case 2 show you a ground acceleration with 20 Hz. Case 3, 10 Hz. Case 4 show you not a pure sine acceleration, show you ground acceleration with complex shapes. And have a look of these calculations. I try to calculate the frequency ratios. Case 1, the frequency ratio is 0.8. Case 2, the frequency ratio is 0.4. Case 3, the frequency ratio is 0.2. And go back to the previous slide. We mentioned that our device, the applicable range, is for beta less than 0.5. You can have a look of this outcome. The actual values is shown using the solid line. The measured value measured by our machine is shown that using a dashed line. You can see that for relatively large frequency ratio, our measurement is somehow lesser as compared with the actual values, which means that our device is not that accurate when you measure this frequency, 40 Hz. When you scale down the frequency, what I mean is that when the ground acceleration frequency is smaller, 20, then the frequency ratio is 0.4. It seems that the two curves are quite similar. So that means our instruments, our accelerometer, is good to measure this frequency of ground movement. Although there are some time shift, but the time shift is not our interest. It can model the amplitude, it can model the shape. That is good enough, right? For even smaller frequency, the accuracy is also very good, as long as beta less than 0.5. So show you the meaning of the previous descriptions. The records, the readings really depends on what frequency you are measuring for your situations. And the last situations, case 4. Case 4, if you use this device to measure a ground acceleration which is not a pure sine function, just like these shapes. I don't know how to describe these shapes, but it's just like mixing different sine function, right? Mixing different sine functions together. And it seems that the dashed line is quite similar to the actual situations, which means that this device is also good to measure very complex shapes of ground motion. Not only pure sine, not only pure cosine. It's also applicable to measure a ground acceleration with complex shapes. At least better than nothing. Okay, this is the idea of accelerometer. We can develop this kind of accelerometer using the concept of spring mass vibration under harmonic vibrations, under harmonic loading. The last applications, forced transmissions or vibration isolation. Actually, there are two concepts, two applications, but we group them together. We group these two concepts together because they follow the same equations. So we put them together. There are two situations. Firstly, you may take a look of the first picture, picture A. Picture A. Suppose we have a table. On the table, it's with a beam supported by two columns. On these structures, we have a heavy machine. When this machine operates, it will generate a dynamic force. It will generate a dynamic force. It may be horizontal or vertical, depends on how you put your machine on the structures, on the slab or on the beam. When this machine oscillates, it will generate a dynamic force, pushing the beam or slab moving up or down or horizontally. Sometimes we would like to measure how many forces will be transmitted to the supporting structures. Supporting structures mean the beam or the slab or the column. We would like to understand the force transmitted from the machine to the supporting structures to avoid any damage occurred on the supporting structures. This idea is called force transmissions. We would like to calculate how many force will be transmitted from the machine to the supporting structures to avoid any damages occurred on the supporting elements. This is the first type of problems. We call it force transmissions. Second, case B. Case B is talking another scenario. It's not talking about force. It's talking about the ground acceleration again. Suppose we have the same problem. We have a structure. This structure, there's one very sensitive equipment sitting on these structures. These very sensitive instruments, we don't want this instrument to be affected by the environment. But unfortunately, there may be some movement of the ground due to heavy vehicles or due to earthquake, due to any human activities. When this ground move, this movement may probably transmitted to the structures and then to the instrument. This ground movement will affect the performance of this very sensitive instrument. So there's another problem. We would like to know how many the amount of ground movement transmitted to this instrument from the ground level to the instrument levels. So this problem is called vibration isolation problems. We would like to know how much amount of ground movement will be transmitted to the structures. We want to avoid this occur. So we have to do something. We call that isolation. We have to do something to prevent this large vibration transmitted to the instrument. So you can see the direction are actually opposite. The first problem A, we talk about force transmissions. When this machine operates, the force will transmit it to the structures, make its damage go down. But the second case B is talking about the opposite directions. When the ground display, it will shake the instrument. So the transmission direction is something like going up. There are two different problems, but why we put them together? Because after some deliberations, we found that these two different situations are governed by the same equations. That's why I put it under the same topic 4, the last applications. We start to introduce this concept using force. Force normally more easy to understand because we play with force for a long time. Force transmissions. Don't need to worry about the terminology because in these sections we keep using this spring mass system. Okay, the problem seems complicated, right? We're talking about structures, talking about some device, etc. But actually, all the things we are using spring mass system to model the structures. For spring mass system, something like this: a mass attached by springs by damper. For this kind of system, you can always convert them back to this Ball and stick model. For ball and stick model, they are only characterized by 3 dynamic properties, MCK. So you know the equation, you know how to solve it, as long as loading is simple. At this stage, you know how to deal with free vibration and harmonic vibrations, so the solution is not that difficult. Let's consider a spring mass damper system under harmonic force, harmonic loading. The force transmitted to the base level is equal to what? Take a look on this problem. A spring mass system under a sinusoidal force. At the ground level, we have a force. I call this Ft. Ft is the total force at the ground level. The force is due to 2 parts: the stiffness component and the damping component. When you take a look on at the picture on the top right-hand corner, we have spring, we have damper. Each will transmit some forces to the supporting level. So the total force at the base level composes of 2 parts: the elastic force due to the spring and the damping force due to the damper. And elastic force, based on our discussion in topic 4, elastic force is equal to stiffness times displacement. Again, according to our viscous damper assumption, damping force is equal to damping coefficient C times velocity. If you know displacement, if you know velocity, then you can calculate the total force at the base level at any time instant. This is the meaning of these equations. Then what is displacement? What is our velocity? We know the response at steady state. At steady state displacement, we know their values. The displacement at steady state maybe I put it again, is equal to UST times RD times a psi function, something like this. Okay, this is our steady state response, displacement. You can recall this formula from the previous session 1. So you can see that the displacement U is equal to UST RD times psi function, and then multiplied by the constant K, give you the elastic force. Then what about velocity? U dot. By calculus, you can differentiate our displacement function with respect to time to get our velocity equation. UST RD omega bar cosine omega bar t minus phi. Calculus. The d sine give you cosine. And then you have to drag omega bar outside these cosine functions. So you can also find out our expressions for velocity. If you like, you may also find out the acceleration using calculus. Differentiate once more time. So although the notes just give you our displacement equations, but actually you can extend the idea to velocity, to acceleration, to the other things. Okay, same concept. And so we have these equations. Using this equation, you can calculate the force at any time instant. You just put t equal to your target time instant. Then you can find out the values ft. But again, from our civil engineering applications, we're not that interested to know what happened at the middle. We just want to know what will be the maximum value. What is the maximum force? If you want to check whether damage occurred or not, then you just compare the maximum force with the strength, with the capacity of something. So how to find out the maximum value of this equation? Again, if you like, you may use the idea of calculus, right? D the function and then set is equal to 0. You may use it if you like. Here I give you the outcome directly. The maximum force, maybe you can call this force amplitude. For amplitude, we normally use a subscript 0 to denote that it is the amplitude of something. The subscript 0 here means the amplitude, the maximum number. The maximum number is equal to UST RD times square root k squared plus c squared omega bar squared. Omega bar is the loading frequency. K, C, they are those coefficients. RD, we know how to find out RD. UST, P over stiffness K. So by using this equation, you can directly evaluate the maximum total force transmitted from the machine to the supporting structures. Normalize the total force amplitude by our force amplitude P0, then you can get this equation. RD, square root 1 plus 2 damping ratio omega bar over omega n squared. This part actually is our frequency ratio. 2 damping ratio times frequency ratio, beta, and then take the square. Okay, this is the equations for force transmissions. Total force versus the force amplitude P0 is equal to this part. We know we have the equation of RD. If you like, you may also put the equation of RD into this equation to make it more simple. We give this ratio a special name. We call that transmissibility. We call this ratio total force amplitude over the applied loading amplitude. We call this as TR, transmissibility. The amount of force transmitted to the supporting structures, we call that transmissibility, TR. TR, by definition, is equal to total force over the applied force amplitude, and then it can be calculated using this complex equation. This equation is from the previous slide here. This one. I just substitute the definition of RD into these equations. You can use this equation to evaluate how much force will be transmitted to the supporting structures. How to use this equation? From the given structures, I believe that you can calculate damping ratio, or I should say in this way, you can evaluate damping ratio yourself. You can evaluate frequency ratio yourself. That's why you can directly calculate what happened on the right-hand side of this equation. This equation just depends on damping ratio, depends on frequency ratio, nothing else. Two things, damping ratio and beta. By definition, beta is equal to omega bar over omega n, frequency ratio. So you can calculate transmissibility based on these equations. And then P0. P0 is the force amplitude, right? The force amplitude, the applied loading amplitude, right here. Suppose you can evaluate the applied force amplitude, you should have some way to evaluate P0. So by using this equation, the total force is somehow equal to TR times the applied force amplitude. Then you can estimate directly how much force will be transmitted at the ground level, at the support level. Okay, we call it transmissibility. It's a very efficient equation. Better than from the first principle, right? If you want to calculate from the first principle, then you need to do this calculation yourself. It's not that easy because you have to figure out the time instant to get the maximum value. Not easy. What about the graph? The graph just showed you the change of TR with different frequency ratio. You have seen a similar graph before in the previous sections, but this time we plot the graph using TR, not RD. Last time we plotted in terms of RD, but here we plotted using transmissibility versus frequency ratio, beta. Different color represent different damping ratio. 0.5, 0.05, 0.2, 0.5, and 1 damping ratio. And again, you can see that at the beginning, it seems to us that at the beginning, when beta equal to 0, it seems that TR is equal to 1. That means actually the first point with beta equal to 0 indicates static, right? The first point indicates static. The loading doesn't oscillate, which means static situations. For static situations, equilibrium, force should be equal. That's why the factor is equal to 1. It makes sense. When beta increase, TR increase. That means the loading transmitted at the ground level will be n times bigger than the applied loading amplitude due to dynamic effect, due to magnification effect, something like that. When loading increase further, up to around frequency, up to around beta equal to 1, resonant, you expect to have maximum force at the ground level, and then the value decrease. As time goes on. Okay, this is about what we how to understand this picture. So for force transmission, the first type of problems, we know how to evaluate the force transmitted at the ground level using transmissibility. Although it's not complicated, but the equation just involves two parameters, beta and damping ratio. You may use it directly. Then what about the second problem? The second problem, vibration isolation due to ground movement. This one, the derivation is slightly complicated. The second type of problems, phase isolations. Suppose you have a very sensitive machine. We don't want that machine will be affected by the ground movement. So you have to calculate the ground movement transmitted to the machine level. How to do so? You can model this problem using a ground movement equations. We use the ground acceleration again, just like that you saw before in the third application. We assume that the ground movement can be modeled using ground acceleration, U double dot G, psi function. Although the ground movement is not necessary to be a psi function, but to derive things, we have to make the situation more simple. Otherwise, you cannot set up one closed form solutions. So when this ground display, the machine, the sensitive instrument located on the top, right? We would like to know how much of the ground movement will be transmitted to the upper level, to the machine level. So actually you are asking to find out the total acceleration fielded by the object at the top. You would like to calculate the acceleration experienced by the object, the machine, at the top level. So you're asking to find out U double dot t, which is the total acceleration. Total acceleration, according to our discussion in topic 4 again, this picture is obtained from topic 4. Topic 4 talk about formulations. Topic 4, for structures under ground movement, we have two components. One is the ground movement components. The other one is the relative movement of the structures. Total displacement means the summation of u plus ug. Same for acceleration. Total acceleration is equal to the ground acceleration plus the relative acceleration of the structures, two parts. So if you want to know the acceleration fielded by this object, you have to find out the ground acceleration. Ground acceleration is some given number. Ug, E double dot G is given. Something appeared at the ground level. You can measure Ug using accelerometer. U double dot is the acceleration that you need to calculate by solving this differential equation, by solving this equation of motion. But if the loading is a psi function, if the loading is a psi function, that means you are talking about harmonic vibrations. You know the result of harmonic vibration. So actually you don't need to solve it. We have already solved it for you in the previous sections. Displacement at steady state can be expressed using this formula. I think this is the third time we saw this formula. Right? The first part is UST times LD times psi something. Steady state solution, displacement. You can differentiate this equation with respect to time twice to get the acceleration. And then you can put it to our total acceleration formula. So you have ground acceleration, you have total acceleration, you have ground acceleration, you have relative acceleration. Put them together, it becomes your total acceleration. The acceleration fielded by the equipment is not quite complicated for this part, the isolation, ground movement. In fact, there should be some step before transmissibility to the solution before. But I skip those steps because those calculations are quite complicated. Those derivations are quite complicated. Just like the previous problem, this equation gives you the acceleration at any time instant. We would like to know the maximum acceleration, not any time instant. We would like to know the maximum value of the total acceleration. So actually you have to do many derivations to find out what is the maximum value of U double dot T. This part is quite difficult, quite lengthy. So here I directly give you the outcome. Rather than show you the derivations. If you like, you may go back to the textbook. The textbook was written by A.K. Chopra. It showed you the derivations in details. I remember that they take around 2 to 3 pages to derive the equations. I prefer to skip it right here. I give you the formula. The ratio between the total ground acceleration, the ratio between the total acceleration of the system over the magnitude of the ground acceleration. This ratio, the denominator is the amplitude of the total acceleration that you want to calculate. The denominator is the amplitude of the ground movement, U double dot G0. So this idea, this ratio is just like what we facing before. Ratio between force, right? The denominator is the force, something that you want to calculate. The denominator is something like the applied loading, applied situations. We use the same hypothesis to derive this transmissibility TR. TR is divided by the ratio between total acceleration amplitude. The denominator is the ground acceleration amplitude. And we found that this ratio is equal to the same equation, TR. Same equation, TR. Same as the situations for force transmissions. This equation is also true for displacement. It's also true for displacement ratio. that's why we put them together in the same section. How to calculate the total acceleration fielded by an object? Very simple. You can use transmissibility. Firstly, find out the value on the right-hand side of this equation based on damping ratio, based on beta. Find out the values of TR first. And then you can see that TR times the ground acceleration amplitude. It will give you back the total acceleration amplitude fielded by the object. You can use this equation directly rather than solve it from the first principle. Later on, I will show you some examples to see how we can use this equation to find out the total acceleration of something. Here, not later. Here, one example to show you how to deal with transmissibility problems. Suppose we have a sensitive instrument with weight equal to 45.4 kg installed at a location where the vertical acceleration is 0.1 g at frequency equal to 10 Hz. Well, simply speaking, we have a sensitive instrument sitting on a platform. The mass of this instrument is 45.4 kg. This instrument is mounted on a rubber band with a spring with a damper. The spring stiffness, K, is given here. The damping ratio of the damper is also given, 10%. So you know K, you know damping ratio. This location is under vertical acceleration. The acceleration amplitude is 0.1 g amplitude, which means symbolically u double dot g0 is equal to 0.1 g. G is the gravitational field acceleration. The frequency is equal to 10 Hz. You can transform the statement to something like a picture, right? Help you understand what you are doing. We have a machine sitting on the ground level, sitting on a platform. This platform is under vertical movement. This machine is supported by a rubber band. This rubber band involves a spring, involves a damper with damping ratio 10%. So when this ground oscillates up and down, the vibration will transmit it to this sensitive instrument through the spring, through the damper. The spring and damper will amplify or reduce the ground vibration. Make it bigger, make it smaller. Depends on how you set up the parameters here. What we're going to do, part A, find out the acceleration transmitted to the instrument. Part B, if there is a limit for our total acceleration, we don't want the machine affected by the ground movement. So here we set a tolerance. If the tolerance of the instrument is only up to acceleration of 0.005 g, if we have one upper bound for our acceleration, then ask you to make some modification for the system. These are what we are going to do. Maybe I give you 1 minute to have a look at the problem again. You may think about how to solve part 1 and part B, part 1A and part B. We just learned the concept of force transmission and vibration isolations. This problem, it seems that it's nothing to do with force, right? There's no force element in this problem. So actually, this problem is something related to ground acceleration, related to vibration isolations. So you may go back to have a look of the previous part to see how to use the transmissibility to solve this problem. It's not complicated, but if you understand the concept, then just a few steps. At least I think it's better than simplest method. For simplest method, the problem is simple, but maybe you need to take 30 minutes or 1 hour to solve the equations. For dynamics, the problem may look complicated, but once you understand the concept, for dynamics, at least for single degree of freedom, I believe that you can find the solution within something like 5 minutes to 10 minutes. At this stage, the solution is also straightforward for single degree of freedom system. For single degree of freedom system, normally a few steps, you can get the answer. But later on, when we talk about multiple degree of freedom system, MDOF, then the solution again becomes complicated. Because later, when you learn multiple degree of freedom system, you will see your old friends again, matrix. For multiple degree of freedom system. For matrix, the calculation become slightly complicated. Okay, I think 1 minute's gone. Let us take a look of the solutions. Well, graphically, in these questions, what we're going to do. In these questions, you are asked to find out the acceleration filled by the object. Maybe I call this U T. For sure, we would like to know the maximum value. We would like to know the maximum acceleration filled by the instrument. How to find out the total acceleration filled by the instrument? Go back to the previous page here. Our target is to evaluate our total acceleration filled by the object. And the problem I give you the amplitude of the ground acceleration, common G, something like that, right? Then what about the right-hand side, TR? TR, if you know damping ratio, if you know frequency ratio, then actually you can calculate TR directly. Damping ratio, 10% according to the questions. Frequency ratio, you have to calculate yourself. By definition, frequency ratio equal to omega bar over omega n, the natural frequency of the system. So it seems that we have sufficient data to find out our informations. Beta, by definition, beta is equal to omega bar over omega n. In the questions, I give you omega bar, which is 10 Hertz. Now be careful about the unit. This frequency, this exciting frequency, is expressed using Hertz. We normally use radian per second in our discussion before. So you have to transform the unit yourself. You may transform frequency to Hertz or transform the frequency to radian per second. Make sure that the unit consistent. But at least omega bar, we have some idea about the values on 10 Hertz, something like that. Omega n, we call that natural frequency. Natural frequency depends on K, depends on mass. Mk, we have mass, we have K, so you can calculate omega bar yourself. So beta is something that you can calculate. If you know beta, you can calculate TR. If you know beta, if you know damping ratio, you can calculate TR. If you know TR, then the problem solved because we noticed that the total acceleration amplitude over the ground acceleration amplitude is equal to TR. So just rearrange the equation a little bit, then you can get the U double dot T easily. So solution for this part A. Part A, we calculate some dynamic properties, omega n. Omega n, by definition, it is equal to square root K over m. K is given, m is given. So taking the ratio and take the square root, you can get our natural frequency. 17.57 radian per second. Be careful about the unit. When you use this equation, the unit automatically equal to radian per second. Radian per second. The given problem, the noting frequency, omega bar, is 10 Hertz. So we have to change the value to radian per second. Change the value to radian per second. Okay? How to change the value from Hertz to radian per second? Multiplied by 2 pi. Multiplied by 2 pi. I think I give you one equation in topic 5. I give you the transformation equation in topic 5. You can transform the value between frequency in radian per second, transform to frequency to Hertz. Hertz mean what? Hertz physically, the unit Hertz mean number of cycle per second. Number of cycle per second Hertz. Omega is also talking about frequency. The radian, the revolution in terms of radian per second. And we notice that one revolution One revolution has 2 pi radian. So you can multiply 2 pi to transform the unit from hertz to radian per second. Unit transformations. Taking the ratio, you can get the frequency ratio, beta. Remember the definition carefully. Exciting frequency at the top. Exciting frequency at the top. The numerator is exciting frequency. Do not reverse the definition, otherwise you will get totally different things. Excited frequency over natural frequency gives you frequency ratio 3.58. It seems that it's a big number, 3 point something, quite far away from the resonant level. Resonant is at 1, right? Beta 1 is 3 point something. It seems that it's quite far away from frequency, resonant frequency. So we expect that the value should be a small number. TR, we used the formula before. Use your calculator carefully, then you can get TR is equal to 0.104. Transmissibility is equal to a small number, 0.104. Less than 1, it seems that it is something like a reduction factor. We believe that the total acceleration fielded by the object should be lesser than the ground acceleration amplitude, lesser than this by this number. So what is the total acceleration? Total acceleration, ut double dot equal to TR times u double dot g0. The ground acceleration amplitude is 0.1 g, as mentioned by the problem. TR is 0.104, so the acceleration fielded by the object is equal to 0.01 g. 0.01 g. Okay. It's pretty simple as compared with Sylvus method, right? There's no matrix, no any matrix inverse, matrix multiplications, etc. But you have to read the question carefully to see what they're asking you. For dynamics, we can ask you the questions in different aspects. So part A, we know how to calculate the acceleration fielded by the instrument. Part B. In part B, we have a tolerance for our instrument. To maintain the normal operation of the instrument, we have to make sure that the acceleration should be less than 0.005 g. 0.005 g is our upper bound, our acceptable level. From our calculation, our current acceleration is 0.1 g, greater than our upper bound. So you have to do something to modify your system so that you need to decrease the total acceleration to at least equal to this number. You have to do something to reduce the total acceleration fielded by the instrument. This is what you are asking to do in task B, in part B. Suppose there is one assumption. Suppose you are using the same support system. Normally, how to do these kind of problems? You can take a look at what you did in task A, in part A. In part A, we use the equation transmissibility to calculate total acceleration. Your task right now is to reduce ut. How to decrease the values of ut? From this equation, you have two choices. You are either reduce TR or reduce u double dot g0, right? From this equation, just read from this equation. You may reduce TR or you may reduce the ground acceleration. But you cannot reduce ground acceleration because it is some external effect. You can't reduce the ground acceleration. Right? Ground acceleration, 0.1 g. You cannot change this number. Otherwise, you don't need to calculate the problems. So you can just only able to adjust TR according to this formula. How to adjust TR? According to our discussion, TR depends on two things, beta and damping ratio. You can adjust beta, you can adjust damping ratio in order to reduce TR. But what we can do, It seems that in these questions we have one assumption. Assume that we are using the same rubber pad, same support. This statement actually means you have to keep damping coefficient as the same number because you are using the same support system. Actually, this statement gives you this condition. You have to keep the same support system, which means the stiffness and the damping coefficients should be the same value. You cannot change K. You cannot change C. For a dynamic problem, we have three basic dynamic properties, M, C, K. You cannot change K, you cannot change C, so you can only adjust the mass. Okay, adjust the mass. You may either increase the mass or decrease the mass to change the dynamic property of the system. You change the frequency of the system, change omega n, simply speaking, by adjusting the mass. Change mass, change omega n, then beta change. When beta change, TR change. This is the idea how you can reduce the total acceleration felt by the object. A more direct method, I think, is to observe from the graph here. Oh, this graph is only plot up to beta equal to 3. Our current beta is 3 point something outside the graph. But you can see that you can go further to make the values of TR even smaller. The graph shows you how to change, which direction should go. So here, the solution B, we adjust the mass of the system. How to adjust? Here you have to we rely on trial and error. Actually, there are some steps here. I try to add mass or try to reduce the mass so that to see what happened to the system. Here I directly show you the final answer. Actually, you have to use trial and error. You have to try to increase the mass, increase by 30 kg, 60 kg, or reduce the mass to see the final outcome. Here I directly show you my answer. Assume that we add a mass with mass equal to 68 kg to the system. After several times trial and error, I found that this is our possible solution to satisfy our acceleration limits. We add additional mass to the system. The additional mass is equal to 68 kg. Make it bigger, heavier. So our new frequency ratio, our new natural frequency becomes stiffness over a big mass. We have one additional mass in the denominator. The new frequency ratio is equal. The new natural frequency is equal to 11.11 radian per second. Make it bigger. Beta becomes 5.66 in this case. Increased beta can reduce TR according to the graph before, moving to the right-hand side. Damping coefficients of our support, our rubber pad. This is we have to calculate the original value first. This is the original value, the old value, before adding the mass. Before adding the mass, the damping coefficient is equal to damping ratio 10% times 2 times the mass, the original mass, times the original frequency, natural frequency. This is damping coefficients before adding our mass. After adding the mass in our new system, the new damping ratio, nu, is equal to our original damping coefficients over 2 times a bigger mass times our new frequency, natural frequency. Okay, here we assume that C remain the same. C remain the same because we are using the same support system, same K, same C, same K, same C. But damping ratio depends on mass, depends on natural frequency. So we have to update damping ratio to a value equal to 0.063. Damping ratio is not a fixed value. Damping ratio depends on mass, depends on the natural frequency. So right now you can calculate the new TR. The new TR is equal to 0.04, lesser than the previous answer. And then finally you get a smaller total acceleration, 0.004 g, less than our tolerance. Our tolerance is 0.005 g. It seems that this operation, add one extra mass on the system, can help to reduce the total acceleration felt by the instrument. It's rely on some trial and error. You have to try this value yourself. Here I directly show my final outcome, but actually you have to try different numbers, 30, 40, 50, 60, you have to try different patterns. And hopefully we found that this 68 can help us to satisfy our acceleration limit. Okay. Try to digest the solution here. It's a little bit complicated in these situations. Okay. The calculation relies on one assumption. Assume the same support using in our calculations, which means Kc remain the same. Kc remain the same. Same spring, same damping coefficients of the system. The only way is to change the mass in this case. It depends on the given informations. As a short break. Let us have a break for 5 minutes. Testing. Okay, let us continue our discussions. Before moving on to the new section, we have some reminder to all of you. Firstly, I have already uploaded the assignment 1 solution on Moodle. You may also download this one from Moodle to have a look of the solution. And second, we have completed all our workshops. I will upload our workshop assignment very soon to Moodle. You can submit this workshop assignment before the end of this semester. You have a long time to do before the end of this semester. Same as the lab report. You can submit your lab report before the end of the semester. Okay, but if you have time, I suggest you may do this earlier. Don't wait for the last minute. Before starting the class, I would like to ask you one question. Some students suggest to postpone the quiz to week 11. What's about your opinions? You mean week 12? That means you would like to keep in week 10, am I right? Is it your opinion or for the whole class? That means all the year 3 students, okay? So any objections if we keep our quiz in week 10? Is there any objections?嗱，keep 翻喺個 quiz 喺 week 10有冇問題 ？No change。
阿 Sir， 可唔可以改去11啊？week 11。
但你哋有其他 quiz 喎，係咪啊？你哋有其他 quiz 咯？
好似係。唔係喎，係啊。但係有冇其他時間可以改啊？如果唔想喺 week 10嘅話，但係 week 11又唔得嘅話
，week 9好冇啊？下星期
提早咗。唔好啊，
嗰啲咯。
就係唔想早啊，因為仲有其他功課同埋 test 啊。
因為我係冇理由褪到 week 14去 quiz 㗎，係咪？
咁冇得改喎。
太遲，咁我俾唔切 feedback 你，咁又係冇用㗎嘛，其實。
好咯。
有個咁嘅尷尬情況咯，即係唔係話唔想褪，但係褪到太遲咧，咁我睇唔切你哋啲 result 咧，咁我俾唔到 comment 你哋啊。
OK。
keep 翻去 week 10好冇？week 10再下個星期。
冇問題啊。
Week 10 mean we will have a quiz in on 3rd of November.
阿 Sir， 咁嗰個 A4 紙係咪只可以第一張啊？
係一張 A4 紙兩邊。You can bring one A4 paper. You can read anything on the A4 paper. You can write down equation, write down example, write down essay, write down picture, write down everything on one A4 paper, 2 pages, 2 sides, OK?
OK， 唔該晒。
我哋都可以寫乜鬼落去都得嘅，你畫圖啊，你 example 啊，你寫落去我唔介意嘅。總之一張 A4 紙。You can prepare that note sheet yourself using your handwriting, or you can use PowerPoint, PDF. I don't mind. You can prepare using computer. Yes. You can find out all the formulas from the lecture notes or examples. I will give you some matrices. Trust, beam, or frame matrix. I will give you. problem. It doesn't matter. I can upload my formula sheet on Moodle. Okay, maybe I repeat a little bit. In the question paper of the quiz or final examination, I will give you some standard matrices for trust analysis, beam and frames. Okay, so you may decide what to put down in your note sheet. And other reminder is that I don't know how to explain in English。咁但係有同學佢上次張 note sheet 咧就佢貼咗好多 memo 紙喺上高度。Last time some student they put many they stick many memo paper on the note sheet. Try not to do so. Okay, try not to do so. What I want to mention. Next week is week 9, right? Today is week 8. Next week is week 9. Week 9, I will give you some tips how to prepare the quiz. So try to attend the lecture next week. You may remind your friend if they are not here. There are only 19-something students in these sections. Yeah. For those kind of tips, normally I just record my presentation for the lecture materials. For this kind of discussion, I will not take the video records. So you may remind your friends if you like. Okay, so finally our decision is that we would like to keep our quiz to week 10. At least you can bring an A4 paper to the quiz. So I believe that it may somehow release your pressure a little bit. And the quiz only cover contents up to topic 5, free ribations. So the materials that we discussed today is not included in the quiz. Okay. The material for the quiz has already covered last week. So I believe that you have long time to prepare this one. Not that difficult, don't worry. But one reminder is that the quiz is face-to-face. There is no online version. You have to come back and take the quiz physically. Okay, no online version. If you feel not very well during at that time, try to see a doctor, receive those relevant documents. Then you can take another supplementary quiz later. You know the situation is quite complicated nowadays. We have COVID-19 or the other matters. So try to prepare those relevant documents if you really cannot able to attend the quiz. Okay, but I believe that should be okay. Because for your general education module, I believe that all of you need to come back to school. So at least you can enter the campus. So this is something I want to mention before the next sections. Okay, we keep the quiz in week 10. The day of the quiz is 4th of November. I will give you some information about the quiz next week, so try to attend the quiz. And let us continue our discussions. We not yet finished topic 6. Topic 6 is relatively lengthy. Because topic 6 covers force derivation. The force can be any force. So far, we just consider harmonic loading. Up to now. Harmonic loading means a sinusoidal force or cosine force. But you can see that force can be any pattern. In section 3, starting from section 3, we would like to discuss what happens for the system if you have another loadings other than sinusoidal force. Section 3. I think in this section, we would like to handle a special loading called unit impulse. And then we will introduce one very famous principle. We call it the Hammer integral, which helps you to handle very general situations. Firstly, what is unit impulse? Unit impulse, symbolically, we normally use this symbol, delta, to denote unit impulse force. Graphically, unit impulse force is something like this. We have a loading history. There is no loading right here, except a small durations. The duration of this, we call it unit impulse. The duration is equal to a small number, we call it epsilon. The height, the magnitude of this strip is 1 over epsilon. If epsilon is a small number, then you can see that the amplitude of this force is very, very large, 1 over a small number, a big number. When you integrate the whole loading along the whole time domain, you will get a number 1, a value 1. Integrations mean what? Integrations mean finding out the area of the graph, right? Find the area of this vertical strip, give you a value equal to 1. That's why we call that unit impulse. The area of the pulse is equal to 1, unit impulse force. This force is very important. This force gives us a very useful outcome later, because from this simple picture, some researchers found out some way to handle general loading, arbitrary loading. You will see that wonderful theory on the next slide. But at least we have to deal with this unit impulse force first. Suppose we have a single degree of freedom system under a unit impulse loading, not a psi function right now, it's a pulse loading, delta. We try to solve these equations. How to solve it? You can. I give you one picture to show you the displacement history. This is the displacement history. It's just like a sine or cosine oscillation from the graph here. We have seen this oscillation before in topic 5. Unit impulse response. By definition, not by definition, by solving the equation, we found that the unit impulse response, U, is equal to 1 over m omega d, the damped frequency, times exponential function, times psi something. How to solve this problem? Actually, this problem can be solved using the response of free vibrations. Response of free vibrations. Take a look on this picture. When you consider a time instant slightly after the unit impulse force, say for example here, if you consider a time instant slightly after the application of the loading, what is the value of loading right here? The loading is equal to 0. The loading is equal to 0. For structures under 0 force, then it belongs to free vibrations. We discussed already in topic 5. Topic 5. So you can recall the formula, the displacement for free vibration in topic 5. We directly put it here. What you have to do is to, you can see that the unit impulse force, just like giving us some initial conditions. When a structure undergo free vibrations, to make it oscillate, you need two initial conditions: initial displacement or initial velocity. Initial displacement or initial velocity, so that the structure will oscillate